In this video, we're gonna talk about the extreme value theorem, and it's gonna be the extreme value of the function. The extreme value of the function is gonna be the thing that we have different from the local maximum and the local minimum, and it's gonna be on the closed interval. So it's not going to be on the whole domain of the function. It will be determined under the assumption that we are working on the closed interval. So you see that we have the graph of the function on the closed interval AB, as you can see here. And you see that we like to know where is going to be the highest of this graph in the interval AB, and we're gonna like to be the lowest to determine the lowest of this graph on this interval AB. So this is the key thing that we're gonna study in this section. So I'm gonna put the interval AB here, and as you can see, this one you're gonna have the peak or the highest. So this guy will be the highest point of this function over the interval AB, and for the lowest point, it's gonna be on the other end here. That will be the lowest point, and you're gonna have AB. Okay, so it's gonna be AB in this one. So you see that the highest one happen here. So this one gives you the highest point, and another end will give you the lowest one. So this one will be the lowest point. We're gonna have a name for them. So for the highest one, we're gonna call this guy absolute maximum. Okay, so we have absolute maximum happen at this point. Okay, and we're gonna have absolute maximum. For the second one, you have absolute maximum happen at the what is called the left end. Okay, so absolute maximum. Okay, so this one absolute maximum. By the way, you'll be able to call this guy absolute minimum, and this guy absolute minimum. Okay, so this one we have minimum. Okay, and another thing that I want you to notice will be, you see that in the first example, for absolute minimum and absolute maximum, you're gonna see that if you compute the derivative of this function, it's gonna turn out to be 0. So they are critical number in this case. Okay, so they are critical numbers. So this guy and this guy are critical number. Okay, so they are critical number. However, here you have this point and this point. We're gonna say that this guy are endpoints. Okay, so this guy are endpoints of the interval. So in this case, we may conclude that the absolute maximum, absolute minimum will happen at the point where you have the critical numbers, or the point where you are at the end of the interval A and B. Okay, so this one is going to be the way to test for extreme value. The first one will be, we're going to find all critical point of the function f in the interval AB. We're going to find the value of f at each critical point. Okay, and you're going to find at the end points, it's going to be, you're going to find FA and FB. So they are at the end point of the interval AB. The largest of the value in step 2 is called the absolute maximum, and the smallest of this value is the absolute minimum. Okay, so this is how we determine absolute maximum and absolute minimum for the given function. Let's do this one. I would want to emphasize that the thing that we are working right now turned out to be inside the interval. Okay, so we're not gonna go outside this interval. So everything will lie in the interval AB. Okay, so you have to determine the absolute maximum and absolute minimum value of the following function. So you have fx equal to negative x cubed plus 6x squared minus 5 on the interval 1, 2. So you're gonna find for the first step, you're gonna differentiate. Okay, so you're gonna differentiate this guy. So you have f prime x, so you have f prime x given by negative 3x squared plus 6x plus 12x. Okay, so it's going to be plus 12x equal to 0. Okay, so you just pull out negative x. So you get x plus 4 equal to 0. Okay, so in this case, sorry, it's not plus 4, it's going to be minus 4. So you get this one and you're going to solve for x, so it's going to be x equal to 0 and 4. However, we're going to only the point that you are in negative 2 and 2. So it's going to be x that lie between negative 1 and 2. So in this case, you're gonna not answer 4. Okay, so this one is okay. This one is outside this interval. Okay, so this one will be your step 1. For step 2, we're gonna compute the value of the function at the critical numbers. So we have critical number x equal to 0. Okay, so you have critical number x equal to 0. And you're gonna have the endpoint, which are negative 1 and 2. So you're gonna determine f negative 1, f2, and f0. Okay, so you have f negative 1, f2, and f0. So in this case, okay, so in this case, you're gonna have negative 1 to the cubic power plus 6 negative 1 square minus 5. Okay, so this one you're gonna get equal to 2, right? Because you get 1 plus 1, yeah. And for 0 is easy, it's gonna be negative 5. And for 2, it's gonna be negative 8 plus 6 times 2 square minus 5. So you get 24 minus 13. So it would be 11. Okay, so in this case, you're gonna get the absolute maximum. Okay, so you see that this guy will give you maximum and minimum respectively. So you're gonna get absolute maximum equal absolute maximum value. This guy will be absolute max value, and this guy will be absolute minimum value. Okay, so this is what you have for absolute max and absolute min. So this one is gonna turn out to be your third step. So you just compare the value that you have and you get absolute max and absolute min respectively. The next one, you have fx equal to square root 5 minus 4x on the interval negative 1, 1. So you differentiate this guy in order to find the critical number first. So you have f prime x equal to 1 over 2 root 5 minus 4x, and you dip inside, you get negative 4, and you're gonna solve for 0. So you would get negative 4 equal to 0, so you get no solution. Okay, so we not have the derivative equal to 0. But it's not going to be just derivative equal to 0. We can looking for the critical number from the place where you have the derivative is undefined. Okay, so you see this guy, f prime x is undefined or does not exist when 5 minus 4x equal to 0. Okay, so when 5 minus 4x equal to 0, so you get x equal to 5 quarters. However, this one is outside negative 1, 1. Okay, so this guy is outside negative 1, 1. So we reach the conclusion that we have no critical number. Okay, so we have no critical numbers in this case. And then you're gonna compare only the point on the boundary. So you're gonna compare the point at the endpoint. So we're gonna compute. Okay, so this one is the first step. And the second step turned out to be, okay, so the second step turned out to be here. Okay, so you're gonna compare f negative 1, f negative 1 equal to square root 5 minus 4 times negative 1. So it's gonna be root 9 equal to 3. And you have f1 equal to 5 minus 4 times 1 equal to root 1 equal to 1. Okay, so you get absolute maximum and absolute minimum, okay, respectively. So this one is your third step that you determine for absolute max and absolute min in this case. Okay, so this one will be your third step. Okay, so we're gonna do another one more. Okay, so you have fx equal to e to the x sine x on the interval pi over 2 to pi. So you compute the derivative for this function. So you get f prime x equal to e to the x sine x, so you have to use the product rule here. So it's going to be the first derivative of the second plus the second derivative of the first. So this guy will be e to the x cos x plus sine x. Okay, and this guy equal to 0. And you see that since e to the x never equal to 0, so we're going to have cos x minus plus sine x will be equal to 0. Okay, e to the x, you know that the graph is always above the x-axis, so it's never be 0. So in this case, you get sine x equal to negative cos x, so you get negative tan x equal to 1. Okay, so you're gonna say that you have tan x equal to negative 1, and So where are we? We are on pi over 2 to pi. So if you draw the unit circle, so you're gonna get this guy and this guy, and you get the unit circle like this. Okay, so you get the unit circle like this. So in this case, you're gonna have in the second interval, so you get pi over 2 up to pi. Okay, and so you need tan in quadrant 2. So tan x equal to -1, and you need this guy lie in the second quadrant. So you're gonna answer x equal to 3 pi over 4. Okay, so this one is the point that you're looking for in quadrant 2 is a critical number. It's going to be only one critical number in this case. So this one is your first step. For the second step, I'm gonna have to compare three values. So you're gonna compare the place where you have the critical number. So you're gonna compare, you're gonna compute f 3 pi over 4, f pi over 2, and f pi. Okay, so you need to compute these three numbers. So f3 pi over 4, you plug into the original function. Okay, so you're going to plug into the original function, you get e to the 3 pi over 4 sine 3 pi over 4, and f pi over 2, so it's going to be e to the pi over 2 sine pi over 2, and the last one is e to the pi sine pi. So e to the pi turned out to be 0. E to the pi over 2, you use your calculator. This guy turned out to be e to the pi over 2 because sine pi over 2 is equal to 1. So this guy is about e to the pi over 2. So it's going to be about 7.46. Okay. And for this one is about 4.81. Okay, so in this case, you're gonna see that we're gonna have the smallest one, okay, happen on the endpoint. Okay, so it's gonna be absolute minimum value. So this guy will be absolute minimum value, and you're gonna get the absolute maximum value. Okay, so for no, it's gonna be 7.46 here. So this guy will be absolute maximum value. Okay, so it's gonna be all at the endpoint absolute maximum value. Okay, so this is how we determine absolute maximum and absolute minimum for the given function. And you see that you compute the value at the critical numbers. Okay, so in this case, you have the critical number equal to 3 pi over 4, and you're gonna compute the value at the endpoints. So it's gonna be pi over 2 up to pi. Okay, so this is we compute and we then compare in the third step. So in the third step, we then compare. Okay, so this is how we get the what is called the extreme value for the function on the given interval. Okay, so this one is 4.1. Now we're gonna use the technique that we studied in 4.1 in order to deal with the optimization problem. Okay, the optimization problem turned out to be a word problem. Okay, so you may have to read the question, and you may have seen this one in your high school before about the parabola. So this one is similarly, but we're going to use calculus in order to deal with this problem. The first one will be a farmer has 2,400 feet of fencing and wants to fence off a rectangular field. Okay, so you like to have that border a straight river. So this is the first sentence, and what you can imagine will be you're gonna have a straight river. Okay, so you're gonna have a straight river like this. So you get the river here, and you like to fence the uh, rectangular field. So it's going to be rectangular field. So you're going to get rectangle like this. Okay, so this is how you fence this one. And you're going to have X, Y, and X. Okay, so this is going to be your field. Okay, and then you have 2,400 feet, and you like to have the largest area. Okay, so the question asks you to have the largest area. So in this case, you're gonna use all of the fence that you have and try to like have the border that kind of the largest. So in this case, your constraint will be, so your constraint in this case will be constraint will be you must have x plus y plus x, not x is 2,400. Okay, so you need maximum area. Okay, so you need maximum area. So in this case, you solve for y, you would get 2,400 minus 2x. And the area turned out to be the product between the length and the width of the rectangle. So it's going to be just xy. So it's going to be x, and you have y given by, okay, so you have y given by 2,400 minus 2x. So it's going to be 2,400 minus 2x. Okay, so you're going to have the function a equal to 2,400x minus 2x squared, and you have 0 less than x less than 2,400, because that will be the length of the y that you have for fencing in this case. Okay, so it's going to be this one. You have the x is going to be the length of your fencing, so it's going to be not x is 2,400 and more than 0. The next one will be you're gonna do the extreme value for this one for the largest. So you're gonna begin by a prime x. Okay, so you differentiate one time, you get 2,400 minus 4x equal to 0. So you get x equal to 600 is a critical number. Okay. Then you compute the value at a 600, a 0, and a 2,400 to see what's going on. Okay, so you see that when a equal to 600, it's gonna turn out to be what? Turn out to be what is it gonna be? So it's gonna be 600 24,000 minus 1,200, right? So you gonna get, so I plug in here, okay? So I have to take a look a little bit. So in this case, you get how many? 12, yeah? So it's gonna be 12 times 6, so it's gonna be 72 and you have 40. Okay, it's correct. And you have 0 here. And you have a 24,000. So it's gonna be, okay, so it's gonna be negative 24 square. Okay. Actually, you may ask me, hey, it cannot be that because you have x here and you have x here. So you must have x and x not gonna be more than 20, not 20, 1200. Okay, so let me fix this one a little bit. So you just have x not gonna be exist 1200 because you have 2x. Okay, so you have 2x. So this one is gonna be 1200. Okay, it makes more sense, right? And it's gonna give you 0. Okay, so that it's not gonna go lower or negative area. So you get a 1200 equal to 0. Okay, so this one must be correct. And you see that this guy will give you absolute maximum for sure. Okay, this guy give you absolute maximum, and you get the dimension is, okay, so you get the dimension is x equal to 600 and y equal to 1200. Okay, so this one will be just that. Okay. The Okay, so the question asks you about the dimension. So this is the dimension that you will have. The next one, you get a cylindrical can is to be made to hold 1 liter of oil. So you need 1 liter of oil and you get cylindrical can. So you first draw a picture. So you have cylindrical can, straight one. Okay, so you get a straight cylindrical can. Okay, and you're gonna need this one to hold 1 liter of oil. So it's gonna be this one. Let me draw this one and this one. Okay, so this one is your can. I cannot have it's nicer. Can I? Let me choop, choop, this one. Okay, and I try to draw this one in a straight line, and this one it's not gonna happen, I believe. Okay, that's good enough. So in this case, you have R, okay, and you have the height H. Okay, so you like to have the volume equal to 1 liter, and the volume of the can is pi r square H. Okay, so this one is going to be the volume that you can hold 1 liter of oil. So in this case, you'll be able to solve for H in terms of R. So you have H equal to 1 over pi R square. And you like to find the dimension again. Okay, so you like to find the dimension that will minimize the cost of the material of the can. So the thing that I would want to emphasize will be you need minimize. Okay, so you need minimize. So you need to minimize the metal. So you're gonna have to compute the area. So the area that you have is gonna be the area of the lid of the can. So it's gonna be 2 circle. Okay, so it's gonna be 2 lid in this case. So, and it's gonna be the side of the can. So the side of the can given by a rectangle. Okay, so you have a rectangle. So you get the sum of 2 circle together with the side of the can. Okay, so this one is the side of the can. So in this case, you're gonna get R r, and the side has the height equal to h, and you see that you're gonna get the circumference equal to 2 pi r. So this is this guy, this is this guy. Okay, so in this case the area that we're looking for turned out to be just pi r square, pi r square plus pi r square plus the circumference times the height is going to be 2 pi r multiplied with h. Okay, so in this case it's going to be, you'll be able to plug in h equal to 1 over pi r square. Okay, so you'll be able to plug in this h. What color should I use? I should use the green one. Okay, so in this case you're gonna get 2 pi r square, okay, plus, so you're gonna plug in h, so it's gonna be 2 pi r 1 over pi r square. Okay, so in this case you're gonna get 2 pi r square square, and you get, so you gonna get pi cancel and r cancel, right? So it's gonna be 2 over r. So this will be your function. So you now get your function. Okay, so it's gonna be 2 pi r square plus 2 over r, and here you have r positive for sure. Okay, so you have r cannot be negative number, and this one give you the function ar. Okay, so in this case you're gonna differentiate. So you're gonna differentiate. Now you're gonna differentiate, so it's gonna be 4 pi r minus 2 over r square. Okay, and you're gonna find the critical number by letting this guy equal to 0. So you will get 4 pi r cube equal to 2. So you get r to the cubic power equal to 1 over 2 pi. Okay, to cancel with 4. Okay, so it's going to be 1 over 2 pi. And you see that you have r equal to the cubic root of 1 over 2 pi. Okay, so you have r equal to the cubic root of 1 equal to pi. We have to test whether this guy will give you maximum or minimum. However, you see that this one is not on the closed interval. Okay, so we're not gonna test it by plugging in. So we're gonna test by size changing. What is size changing? Size changing is the thing that we use the real number line and you just put the critical numbers. Okay, so in this case, you're gonna have the real number line and you're gonna put your critical numbers in. So you're gonna get 0, which is your endpoint, and you have the critical number is the cubic root. Okay, so it's gonna be a cubic root. So it's going to be the cubic root of 1 over 2 pi. Okay, so in this case, you're going to check the sign of a prime, sign of a prime. Okay, so you're going to plug in for sign of a prime. So you're going to pick x somewhere here. Okay, so you pick x. Let me use other color, would be clearer. So you pick x here, pick x equal to, I don't know what is this number is, but it's not that small. Let me pick x equal to 0.01. Okay, so just pick x equal to 0.01 and you check the sign of a prime. So you use this guy. So it's gonna be for sure, this guy is gonna be negative. Okay, so it's going to be negative because you see that it's going to be about 200 so far. So here it's going to be negative side. And for this one, you just use x equal to 10. Okay, in this interval, you pick x equal to 10. So it's going to be positive. Okay, so in this case, it's going to be decreasing to increasing. So it's going to be minimum. Okay, so this one equal to square root, and not the square root, the third root of 1 over 2 pi gives the minimum metal. Okay, and this one allow you to solve for h. So you're gonna have h equal to what? H equal to 1 over pi r square. So in this case, it's gonna be 1 over pi, and you just plug in 1 over 2 pi to the 2/3. Okay, so this is how we have the solution. So you find the dimension of r and h for this question. The next one is a geometric problem again. We like to find the point on parabola y equal to 2x squared that is closest to the point 1/4. So if you draw a parabola, okay, so if you draw the parabola here, so you get y equal to 2x squared. It's gonna be this guy. Okay, so this one will be y equal to 2x squared. And we like to find a point that closest to 1/4. Let me have 1/4 here. Okay, and you're gonna minimize this distance. Okay, so this one will be the distance d. And we like to find the point xy. Okay, so it's gonna be x y. Okay, and the distance here turned out to be square root x minus 1 square y minus 1/4 square. Okay, so this one is going to be, and you need minimum. Okay, so we need minimums of this guy. However, okay, what is y? We know that xy is on this curve, and this curve has equation y equal to 2x squared. So we know that this curve has equation y equal to 2x squared. So we be able to write y. Okay, so in this case, you're gonna have the given by square root x minus 1 square plus 2x square minus 1/4. Okay, so this one will be the function d that we have, and we're gonna compute the derivative. So you're gonna dip d prime x. Okay, so you're gonna dip d. So you're gonna dip d. You not have to expand. Okay, you not have to expand this one. Be careful a little bit. Normally, my student expand this one, try to do like a nice thing inside, but it's not happen that way. So we're gonna differentiate this one. Okay, so you just write d prime x, and this guy is gonna be 1 over 2x minus 1 square, and you have 2x square minus 1/4 square, and you dip inside. So you dip inside. Let me use other color for dip inside in this case. So you dip inside in this case, gonna be 2x minus 1. Okay, so that's gonna be one term plus 2x squared minus 1/4 times 4x. Okay, so this one is just dip inside. diff inside. Okay, so you see that it's gonna kind of a big term for differentiating inside. So you're gonna let this guy equal to 0. Okay, so you let this guy equal to 0. So you're gonna multiply this term up. Okay, so you multiply this term up. So you end up with only the purple one. So you're gonna get 2x minus 1 plus 8x 2x squared minus 1/4 equal to 0. Let me write something like this to see the color. Okay, so that's why I change the color. And you see that we can solve for x, so it's going to be 2x minus 2 plus 16x cubed minus 2x equal to 0. And this guy disappear. So you would get 16x cubed equal to 2. So you get x cubed equal to 216 or 1/8. Okay. So you're gonna solve for x. So you would get x equal to 1/2. Okay. So you would get x equal to 1/2. And we need to check whether we gonna get the closest. So you need the minimum distance. Okay, so you need the closest one. So we're gonna check for 1/2. Okay, so we're gonna have for 1/2, and we're gonna check for the side of d prime. Okay, so we're gonna check for the side of d prime. So in this case, you're gonna pick one number in this interval. So you're gonna pick x equal to 0. Here you're gonna pick x equal to 1, and you're gonna put them into your purple. Okay, why didn't I put into the purple? Because we know that this guy always positive. We don't care about the sign. Okay, so we don't care about the sign, so this guy always positive, so it's not gonna change our sign. So you just put this x equal to 1 into the purple, and you see that it's going to become positive, pretty clear. Okay, so you have positive on this side and you have negative on this side. So you're going to get something going down, something going up, and this guy will give you minimum as you're looking for. So this one will give minimum distance as desired. Okay, so this one give you minimum distance, and this is how we determine maximum and minimum. Last one. Okay, so last one for the optimization problem. We like to find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So first, let's try to graph the function a little bit. So you have x and y, and you're gonna have a semicircle. Okay, so you get a semicircle like this. Okay, so this one will be semicircle of radius r. So you have r. And if you recall, this guy will be x squared plus y squared equal to r squared. But in this case, you have y positive. Okay, so this guy, you have it above the x-axis. Above the x-axis is mean that if you solve for y, you would get y squared equal to r squared minus x squared. And you're gonna take the square root in order to obtain y. So you're gonna get y equal to, okay, so you're gonna get y equal to square root r squared minus x squared. And we have only for the positive one because you have it above the x-axis. Okay, so this one above x-axis. Okay, so it's going to be above, I should say the article. I said above the x-axis in this case. Okay, so this one is upper semicircle, so you would get positive side. Okay, so you get the positive side. And we're gonna have the rectangle inscribed in this semicircle. So you see that you get a rectangle, and this one will be your x and negative x. So you have x, negative x. Okay, so you have two sides like this, and you're gonna see that this guy will be your y. So you have the area of the rectangle equal to is gonna be 2x. So the length here turned out to be 2x. So this guy will be 2x. Okay, so it's gonna be 2x, and the height here turned out to be y, right? So it's gonna be multiplied with y. However, you're gonna put y equal to this square root here. Okay, so this will allow you to get 2x square root r square minus x square. Okay, and you see that the length of x turned out to be lie between 0 and r. Okay, so x gonna between 0 and r, because x, your x is here. Okay, so your x is here, so you have x between 0 and r in this case. Now we're gonna differentiate and dip a prime x. Okay, so you get the first derivative of the second multiply with negative 2x, okay, plus the second derivative of the first, so it's going to be 2, and this guy equal to 0. So you simplify this one, 2 and 2 cancel. Okay, so 2 and 2 cancel, and you're gonna get negative 2x over square root r square minus x square plus square root r square minus x square times 2 equal to 0, and x and 2 here get rid of. So you see that you're gonna solve this one. This one seems difficult, however, it's gonna be just you see that it's gonna be square root r square minus x square equal to x over square root r square minus x square. Okay, and you multiply this term up, so you get r square minus x square equal to x. Okay, and I forgot square, sorry. So this one I have square, and I have square. Okay, so I have x multiplied with x, sorry, it's gonna be my x square, sorry. So it's gonna be x square, and you're gonna get x square. So in this case, you have 2x square equal to r square. So you get x equal to r over root 2. Okay, so you take root both sides, so it's going to be x equal to r over root 2. And we have only x positive. Okay, positive only because here. Okay, so it's going to be positive only. I'm gonna just write the plus sign to indicate that. So it's going to be positive only. Okay, so you get x equal to r over root 2, and this one is your critical number. Okay, so this guy is the critical number. So we're gonna compute. So this one is the first step. The second step, you're gonna compute a at r over root 2, which is the critical number. Okay, so r over root 2, and you're gonna compute a at 0 and a at r. So it's gonna be at your endpoint. Okay, you see that a at 0 turned out to be 0, and a at r turned out to be 0 also. And you get a equal to a at r over root 2, over root 2 turned out to be 2x, so it's going to be 2r over root 2 square root r square minus r over root 2 square. Yeah, okay. And this guy turned out to be equal to, okay, so this guy turned out to be equal to 2r square over 2, so it's r square, okay, and this one will be absolute maximum. Okay, ABX maximum, okay, so this one will be equal to, not equal to, x equal to r over root 2 will give you the largest rectangle that can be inscribed into this semicircle. Okay, so this one will be the one that we have. Okay, so that's all for the topic of optimization.